This is the Fortran code which I have written to compute the results of numerical integration using the Monte Carlo method, the Trapezoidal Rule, the Simpson 1/3 method, and the Gaussian Quadrature integration technique. The toy model or the test function is this one. I'm going to compute the integral of this function from 0 to 1 or from -1 to 1. This integral is something related to the error function, which is frequently used in different areas of mathematics, such as analytical solution of the partial differential equations. This is the structure of the code. First of all, you need to write these expressions here in any Fortran code. And here is the end of the program. And this part defines the input function. For example, you want to compute the integral of this function. You can easily change this one to this one. And this way, you can easily compute the integral of any other function. Okay, let's keep the first one. Here you define the spatial coordinate x, the distance between two adjacent nodes h, or the step size. F is the function, as explained here. F is the function. All of them are real parameters. Rand is a random number which is used in the Monte Carlo method. Integral is the final value of the integral. Exact is the exact value of the integral. And these constants are used in the Gaussian Quadrature integral approach. These are integers. I is the counter. N is the number of points. M, C, simp, gauss, and trap are switches. You can turn them on or off to activate different integration methods. Okay, let's discuss the first one, which is the Monte Carlo method. And in the Monte Carlo method, as you know, you have to generate many number of random numbers. This part of the code here generates the random number and saves the generated random number in the parameter rand. So first, the integral, the parameter of integration is equal to 0. This one is the exact value. In the Monte Carlo method, you need to change the limits of integration to 0 and 1 used by means of a very simple linear transformation. So here I've supposed that the distance between the limits of integration is 1. So the h, or the step size, equals 1 over n minus 1, because n is the number of points. But the number of intervals between 0 and 1 is equal to n minus 1. So h is the distance between two neighboring nodes in the domain. Okay, the random number has been generated. Again, this is the loop which generates n. N is equal to 101 in this case. Generates 101 different or unique random numbers. Then you need to compute the sum of magnitudes of f at these random points, and simply after computing this summation, you need to compute the average value of the function, which equals the integral. So you add the magnitude of f at many random points, and then you have to divide this summation by the number of points. This is the average value of f in the interval. Okay, then that's exactly, amazingly, that's the Monte Carlo algorithm. In this part, the code writes the final value of computed integral and the exact value and the relative error of the result on the screen. This is the exact value. Okay, let's deactivate this one, and this one. The main advantage of the Monte Carlo method is its simplicity, and the main disadvantage is high computational time. Here you see this one is the computed numerical result, and this one is the exact value, and the relative error is this one. Using 101 random numbers, you may increase the number of generated random numbers. And this result has been generated by computation of the f function in 501 random points. Keep this number 501 in your mind. Okay, the next one is the trapezoidal rule. Here I have activated the trap, and here you see the integral equals 0. The exact value is this number, which equals the square root of pi over 2 times the error function at 1. In the trapezoidal rule, if you review the algorithm, you need to compute the magnitude of the function at all points and add them together regarding some weight factors. So for the first one and the last node, you compute the function itself, and for other points or the points inside the domain, you compute twice the value of f, and then add all of them to find the summation, and then the result should be multiplied by h over 2. H is the distance between two neighboring points. This is this is the algorithm of the trapezoidal rule, and you can find the result. This is the exact interval and the relative error. Let's run the code. Again, using 501 points, the exact value, and you see the relative error. So using 501 points. So in this case, you have computed the value of f function in 501 points. Okay, let's try the next one, which is the Simpson's rule. Simpson 1/3 rule. Again, the integral should be 0. Exact value is similar to the previous one. And here, the weight factors are different. So, for the first or the last node of the domain, you have to compute the function itself. For the even numbers, or this expression here shows the points which their label is even. For example, the second, the fourth, the sixth, and so on. The coefficient is 4. And for other points, which of course are the odd nodes, you have to multiply the function by 2. And then add all these numbers together, and then multiply the result by h over c. And you can write the result on the screen. Let's, again, using 501 points. Pay attention that in the Simpson's rule, you have to use the odd number of points, or n should be an odd number, and in our case is equal to 501. You see again the error. Okay, the last one is the Gaussian Quadrature method, and this here the limits of integral should be -1 to 1. If the limits are other numbers, you can easily change them to -1 and 1 using a simple linear transformation. So the value of this function from -1 to 1 equals twice the previous one, which is this number here, square root of pi times the error function at 1. And again, these are the coefficients, and these points are the roots of orthogonal functions, and you have to compute the value of the f function in these four specific points and add them together using these weight functions. So in this method, you just compute the value of f in 4 points in this version. And you can compare the accuracy of the results in comparison to the previous cases which I've used. I have computed the value of f in 501 points. And this is no special algorithm, I think. It's just a formula. And the result is presented here. And I can run the code to show the result using 4 points, the Gaussian quadrature. Here, please pay attention to the relative error. Now, at the final stage, let's run all of them and on the screen, and we can compare the relative error using 501 points or 501 random numbers. And in the last one, or the Gaussian quadrature, we have just computed the value of f in 4 points. Okay, you see 4 points. The Gaussian quadrature is approximately similar to the first one, which is the Monte Carlo method, based on 501 random numbers. But these, again, the trapezoidal rule is less accurate in comparison to the Simpson's rule. And the most accurate one is the Simpson's rule, using, again, 501 points. As a result, the Monte Carlo method and the Gaussian quadrature method are both simple, but the Monte Carlo method is expensive regarding the computational time. So, for multiple integrations, I recommend the Monte Carlo method or the Gaussian quadrature.